Okay, where does our energy come from? Next slide. Okay, on the left-hand side, these are the supply sources. So you got your fossil fuels are the big ones. We keep talking about fossil fuels, petroleum, natural gas, and coal. We got your renewables, wind, solar, geothermal, and nuclear. On the right-hand side are your demand sectors, transportation, industrial needs, residential, commercial, and electrical power. And this is shown for the United States in 2007 that we used 101.6 quadrillion BTUs, or 10 to the 5th BTUs of energy in the United States. And so what does that mean for the world if we use 25%? What was the world using at this time? 4 times that, right? So somewhere around 400 billion. These numbers in the circles and these numbers in the blocks add up to this 101.6 quadrillion BTUs. So petroleum, you can see, is a big chunk, natural gas and coal. And then the percentages is what do they supply? Petroleum, 70% of that supplies the transportation sector, 24% for industrial, and so on. Natural gas, a little bit for transportation, and pretty much equally divided industrial, residential, electrical. Coal, 91% is electrical power. There's a little bit used for industrial and very little used for residential and commercial. Renewables, you can see the 51, most of it is for electrical power, and nuclear, all of it. We haven't quite figured out how to make a nuclear-powered car or airplane, and probably don't want to. Even though they tried that, they tried to make a nuclear-powered airplane. On the demand sector side, transportation, you can see this one shows 96% of transportation is provided by petroleum, 2% by natural gas, and 2% by renewables. So again, that 98% is coming from fossil fuels. Electrical power, 50% from coal, 20% from nuclear, and then natural gas, somewhere in the, it says 17% here. So does this make sense, where all our power is used? Okay, next slide. Now, if we're just looking at, go back a second. This electrical power section, this 40.6 quadrillion BTUs, go to the next slide. That portion and how it breaks down, here's another way of looking at it. And again, the numbers are slightly different because this is from a different source. We can see about half from coal, 20% from natural gas, a little bit from oil. You add those up, those are the fossil fuel providing energies. And then 19–20% from nuclear, a little bit from oil, and then here's your renewables, not a lot there. Okay, next slide. So let's talk about the future projections. How much energy are we going to need in the future? And this is a little bit sobering if we think many generations out. Next slide. Okay, this was a study that was done that projected out from 2005 to 2030, and it's broken down into this top block as nuclear, renewables, natural gas, coal, and liquids. And you can see that just on a percentage basis, 15,000 trillion kilowatts just by the year 2030, we're over doubling that amount of energy. Okay, next slide. This one's even a little more scary. Remember we were talking about that 400 to 500 times 10 to the 15th BTUs per year that we are right now? Look at the projection over the next couple of hundred years. Now, people can argue with these projections, but clearly we are going to need a lot more energy. And that energy is not, it's somewhat driven by population growth. Our population is projected to be about 9 billion on planet Earth somewhere in this time frame, but we more than double the amount of energy use. And the reason for that is, again, those developing nations using more and more energy. Okay, next slide. Some sobering facts for fossil fuels at current production. And you can argue with these numbers. You can see all kinds of places where they say, how much oil reserves do we have in the world? How much coal reserves do we have in the world? But some studies show that we have enough coal to last another 119 years. That's good for us, our grandchildren, and our great-grandchildren. You start getting beyond a few more generations, coal is not going to be there. The same thing with oil and gas. You know, some studies show more than 100 years based on some of the shale gas. You've probably heard there's different extraction techniques for getting the natural gas that's locked up in the shale, and those techniques are getting better and better so we can get more and more gas. Over 62% of oil and 64% of gas reserves are concentrated in the Mideast and Russia, which kind of speaks to some of the security needs of our country, of what are we going to rely on for energy for the United States. Next slide. Okay, so are we going to have enough? Next slide. This is an interesting slide that, who gave this, Bill? Somebody from the SRNL this recently. And this kind of speaks to that moral conundrum we were talking about. The yellow circles are millions of people without electricity and millions of people relying on biomass. So these are the undeveloped countries where in South America, 56 million people flat are living without electricity. 96 million just relying on biomass. Some of them are burning peat for their fuel source. Peat is essentially a predecessor to coal a few million years back, right? Africa, you can see the numbers. So there are large population densities throughout the world where people are without electricity at all. Okay, next slide. This is a very similar curve I showed you before where we were sitting about 400 or 500 times 10 to the 15th British thermal units per year. And the projection out goes up by a factor of 10 at the year 2300. These curves show coal, crude oil, natural gas, and then the total fossil fuel projections of how much energy is available over that couple of hundred years. And you can see there's a bit of a gap between these two. So obviously fossil fuels are not the answer many generations down the line. Okay, next slide. Impacts of fossil fuel, go ahead. Okay, next one. Okay, next slide. Another thing you hear all about is greenhouse gases and global warming and the connections between our energy production and how much greenhouse gas or carbon dioxide is produced by our various energy sources. And as you would expect, since fossil fuels are carbon-based, coal and natural gas lead the pack with how much CO2 they put out. And this is per gigawatt hour. You can see biomass, solar, hydro, nuclear, geothermal, and wind are very small in comparison. Okay, next slide. Next. Here's another way of looking at it. What this shows is the yellow is the 90s of greenhouse gas emission factors for production of electricity, and the green shows based on efficiencies in the various industries and new regulations that are going in to limit greenhouse gas emissions, what the impacts are expected to come down to 2005 to 2020. And again, you can see that nuclear, hydro, wind, biomass, solar are very small, not so much solar, but natural gas, the fossil fuels, again, are very high, and even if in the improvements, they still produce a lot of greenhouse gases. Okay, next slide. Okay. Everybody has one of these. Pull this out of your packet. It's a little, it says source energy equivalence. Now remember we were talking about energy density. Should be a little packet that shows a fuel pellet. So what does that say? One uranium fuel pellet without being reprocessed and recycled has about as much energy available in today's light water reactor as 3 barrels of oil. How much coal? Ton of coal. And how much natural gas? Yeah. So that little pellet, that's an example of the equivalency of the energy. And that's that energy density thing we were talking about. Okay? And then this slide kind of demonstrates that a 1,000 megawatt electric plant can supply about 500,000 people, and that depends on where you live. It could be more if you're in the South and you run your air conditioning a lot. But uranium, you need about 33 tons each year to supply that. Coal, 2.3 million tons. Oil, 10 million barrels. Natural gas, is that 64 billion cubic feet? Solar cells, 39 square miles of solar cells. And these solar cells and wind is 3 times that much. The reason for that is, again, energy density. The fact that we can walk outside and stand in the sun means there's not a lot of energy density hitting your body, or you need something very big to collect that energy to get the equivalent of what you would get out of coal or oil, and certainly a lot of what you would get out of uranium. Okay, next slide. Okay, we were talking about waste discharges, and this is a direct comparison of a coal plant and a nuclear plant, how much waste is produced per 1,000 megawatts. So if you go back to that last slide a second, that coal plant was using 2.3 million tons of coal. Next slide. And the waste that it produces per year is 1,000 tons of sulfur dioxide, 5,000 tons of nitrogen oxides, 1,400 tons of particulates, 7 million tons of carbon dioxide, and up to 1 million tons of ash, but it's probably, the technologies, it's probably more like 250,000 tons of ash to 300,000 tons. And you can see on the spent fuel side, 20 to 30 tons of spent fuel, which the technology, Bill will get into this a little bit, I think, but it's really a political decision rather than a technology decision on what we do with that waste product. Go ahead.